Yeah, I was reminded by Billy that I should welcome formally everybody to the festival, so let me take this opportunity to do that. So this is the second time we've run an event like this. This is the 2-year anniversary, I guess, of the beginning of MetaUni, for which Lucas was in attendance, I believe, and some of you also. But for many of you, it is a more recent experience, so welcome. So there's going to be a series of talks today. They'll all be around here or in nearby locations. If at any point you get lost and you can't find the talk, just reset your character. So you can click on the Roblox menu and go reset character and you'll just spawn into the right place. And if you have any questions, get in touch with either myself or Blinky Bill. Type it in the chat or in the Discord and we'll try and help out. Alright, so I'm going to begin. So the title of my talk today is The Case for Short AGI Timelines. You may hear chickens in the background. There's nothing I can do about that. Apologies. Alright, so I'm going to say very briefly what I mean by this title and then get into it. This isn't meant to be a super detailed answer to this question. That would take more time. It's meant to be a high-level guide to the way I think about this problem or this phenomena. And there are dedicated seminars that talk about this kind of thing at MetaUni, to which you are welcome to come. I'll say more about that later. Alright, so let me say what I mean by AGI first. So today we have artificial intelligence, things like ChatGPT, GPT-3, AIs that can look at this board and figure out what the text on it is. Most of them that work well are based on something called deep learning. These are not general intelligence. So the precise meaning of general need not concern us exactly, but humans are generally intelligent, and we take that to mean that they can learn to solve a wide range of problems. So an AGI is a hypothetical technology. We don't know how to build it, or at least nobody has built it yet that we're aware of. So it's a hypothetical technology that can learn to solve any problem a human could solve. And to perform any cognitive task a human can perform. I'm framing this in kind of economic terms or kind of technical terms. It isn't about sentience or whether the machine can fall in love or have a deep emotion. Those are somehow much more subtle questions than just can the algorithm perform any economic task in front of a computer screen that you could perform, or any human, no matter how smart, could perform. Alright. Now it sort of goes without saying that if you can produce one such machine, you can probably mass produce it, although maybe that isn't so clear necessarily. But if one can be produced, it's likely it can be mass produced. And that means that the invention of AGI will be a truly historic event on the level of the invention of agriculture, for example, or perhaps even more profound than that. So it's really quite a sci-fi concept, AGI. If it's invented, then the world changes rather rapidly and quite dramatically. Which is why it's so remarkable that many people, serious people, are considering AGI to be a near-term possibility, as in within 10 years or something on that order. So when I say the case for short AGI timelines, what I mean is let's examine the argument for why it's possible that such a technology might come to exist within 10 years. Of course, nobody knows. It could be much harder than any current analysis suggests. It's partly just guessing, right? We don't really understand how we got to the point where we are, so we don't have a good basis for predicting where we're going to go. Nonetheless, what I want to argue for is that it's not ridiculous, right? And even maybe you should assign something like 50% probability to this, which is what I do. So I think that the probability of AGI being achieved within 10 years is greater than or equal to 50%, which is crazy. Okay, so here's a high-level sort of diagram. Let's start with just the question of, is AGI possible? I mean, the A is playing a role here, right? So general intelligence exists. Here we are. We're talking, we believe ourselves to be generally intelligent. But can AGI exist? Artificial general intelligence? You could say no. Right. Now, if you say no to that, then basically that means you believe there's something unknown and very special about human intelligence. I'm not dismissing that. It could be the case. I don't think there's strong evidence for that, at least not that's convinced me. But you could say that, well, maybe the human brain involves quantum mechanics in some way, and it's just or some other phenomena that's extremely hard to find, and evolution chanced on it in some extreme rare event, and without that secret source it just isn't possible to go from our current level of AI to general intelligence. That's possible, right? So to say no to this question, you have to believe in something like that, I think. So I don't find that convincing. I don't see evidence for that, so I'm going to say yes, I think it's possible. If it's possible, the question becomes, is it easy? Now, by easy, I don't mean, is it as easy as installing a game on Steam? I mean, is it on the order of things that we routinely do as a civilization? Right? I mean, setting up sanitation for a city with millions of people is not easy in the sense that it's trivial. But it's a straightforward problem that we can solve by deploying pretty straightforward algorithms sort of executed at sufficient scale and with sufficient attention. Right? Now, to say no to this question would be to say, again, that there's something really tricky about getting to AGI. Now, an example of something I don't think is easy is producing semiconductors. So producing the semiconductors that run today's artificial intelligence is very difficult. It involves many, many layers of highly advanced chemicals, materials, engineering, physics. It's also a sort of human capital problem, organizational problem. That's a hard problem. To say easy here, I'm saying that it's dramatically easier than that to produce AGI, given the existence of the semiconductors. Right? Of course, to produce an artificial intelligence in today's fashion requires a lot of computer science, hardware, and many other aspects of our modern technological civilization. But given that, the question is it easy or not from where we are to get to something that is a general intelligence? Now, to say no here is to say maybe it takes another 100 years, right? Maybe we're waiting for some super difficult idea, and until we get that idea, we'll just be stuck. That's possible. I don't think it's very unlikely, right? It could be the case. It's a genuine possibility. the question you have to ask if you're going down this path is, if you say no, well, why has it been easy so far? So by the standard I'm using, everything to date in deep learning has been easy. And, well, here we are. We have algorithms that seem to be intelligent in some fashion, not quite like us, but getting to here has been easy by my standard. And if you say that no, what happened there? We all got booted. Alright. Back we go. Alright, that was fun.
I heard
I
up
guess
to... Sorry, I was just going to say, I heard up to when you were saying it's been easy so far.
Yeah, okay. I'm glad the boards seem to have saved what they were up to. Okay, there's a few people who maybe were in OrbCam and don't know what happened. I think I'll just continue. Maybe somebody can walk over there and help them out in a minute. Okay, I'll just keep going. Okay, so you could say no to the easy question, but I'm going to say yes because, well, it seems like the simplest thing to say. It's been easy so far. Maybe it continues to be relatively easy. Okay, so let's say yes to that question. I'm going to put more meat behind these choices in a moment. And then the question is, will we do it? Right, so maybe it's possible, maybe it's even easy in the sense we know what to do and it's just a matter of doing it. Will we actually choose to do it? To say no there seems quite perverse, right? Well, okay, there are many things that are possible, even easy, that we just don't want to do because they don't seem to have any particular value. But building AGI seems self-motivating to be... if you can build such a system, it will have immense economic value, military value, and so on. So I think we have to answer yes to this. Okay, and that leaves us down here. That doesn't mean it's less than 10 years, right? I don't know actually a strong argument for why the difference between 10 years, 5 years, or 15 years. We could go into more of that in other sessions, perhaps, but yeah, maybe I'll return to that question of the exact time frame at the end. Okay, so I'm going to go through 3 or 4 kind of high-level points that shape my thinking on these matters. And the first is a kind of fallacy I see people engaging in, which is essentially a form of creationism, or rather the logical fallacy behind creationism. So the reason people rejected evolution is that we have a strong intuition that complex, capable systems can only be produced by more complex, capable systems. Right, when you see an eye, you presume that there is a being which is more complex than an eye which designed it. And it's a radical, surprising fact that this is not the case, right? It is probably one of the most profound things we know that evolution works, namely a simple algorithm. Simple algorithms executed at scale can produce highly complex systems. That's not to say it's easy to find such simple algorithms, or that the scale is easy to produce, but there's an existence proof. Right? It is possible for extremely simple algorithms at scale to produce systems that are much more complicated than the algorithm itself. The intuition people often have about AGI is that, well, somehow to design AGI we would have to be much smarter than that system itself, or something along those lines. I'm not exactly sure how people think about it, but that need not be the case. It may be that we find a simple algorithm that we execute at scale, which is capable of producing an artificially generally intelligent system. That's not to say that any given algorithm we have in our hands or that we find soon is guaranteed to do that, but any argument that gradient descent, the method by which deep learning models are trained, any argument that gradient descent cannot produce, in principle, an AGI, needs to rely on some specific property of gradient descent itself or AGI itself to bypass this objection. Right? In principle, there doesn't seem to be any general reason why it can't be possible. The second thing I want to mention are scaling laws. And this is probably, maybe I'll use the next board. This is the biggest update, I think, that one has to make from the last 5 years of progress. It's a topic that's much discussed here in our seminars, but I think remains underappreciated outside of sort of the technical literature. So I'll say briefly what scaling laws are. So transformer models, so that includes things like ChatGPT, GPT-3, have predictable improvements with scale. Okay, so improvement means test loss. So just very briefly, so a model like GPT is trained to predict the next token, roughly speaking the next word, given a previous sequence of words, say sentences. The test loss is something like it's the number of words it gets wrong. Technically speaking, it's the cross entropy of the next one hot vector of the token with some probability distribution that's output by the model. But roughly speaking, how many words does it get correct? It's trying to drive that to 100%. Okay. With scale means training time, so the amount of flops you spend. Model size, so the number of parameters in your model. And dataset size. So the corpus of language, for example, in GPT that you train on. As you increase the scale, you will get improvements. You will drive the loss to lower values predictably, and predictably means a power law. I won't go into what power laws are. The results of these predictable improvements with scale are kind of predictable. If you can predict improvements, you'll make the investments to get the improvements, and we're seeing that play out with first millions, then tens of millions, and now hundreds of millions of dollars worldwide being spent on training models like this, because people expect to see improvements. Now, I should say that we don't necessarily care about the test loss. right? So this is a measure of how good the model is, but it's kind of technical interest. What's really interesting about these predictable improvements with scale is that these improved measurements of the performance of the system translate to emergent capabilities. And it's these two things together that is the large update. I won't get into what the emergent capabilities are exactly. Some of the original ones that were noticed were that if you train a GPT-like model on text, at some level of scale, it will start understanding how to do addition of 2-digit numbers, 3-digit numbers, even though that's not something it's explicitly trained on. So those are capabilities that we kind of assign conceptual meaning to, whereas the test loss, this kind of sum over errors on predicting the next word in a large corpus, maybe doesn't have a clear interpretation. But these emergent capabilities may. Okay, so these two facts. One, that transformer models, a wide variety of transformer models trained on a wide variety of types of data, have these power law behaviors, scaling laws, and that those scaling laws mean at various levels of scale that you get emergent capabilities. These two things were not expected ahead of time. Transformer models aren't the only kind of machine learning model that have scaling laws. There are things outside deep learning even that have scaling laws, but we don't tend to care about them because they lack this second point. It isn't the case with anything but transformers, as far as I know, that we have a comparable understanding of the emergence of capabilities at scale. And these two things together are, this is a deeply shocking empirical discovery. We don't understand theoretically why this is happening, but this should not be underestimated. I think these two things together, in my mind, seem about as important as the splitting of the atom or something on that scale. Right? We have discovered a new feature of the physical universe to do with learning. Okay, I'm not saying here necessarily that pure scaling is going to get us to artificial general intelligence. It may. Some people believe that. I'm agnostic. So scaling, I really mean quite serious scaling, right? So it's the difference between taking half the internet and like the entire internet as your training data set. Right? We're talking pretty significant scales in order to get the current generation of systems. So you might ask the question, well, what happens if we run out of GPUs? I mean, we can't scale forever, right? What if we run out of GPUs? Is the internet big enough? Do we have enough data to get to AGI? And this question is getting at the point that even if pure scaling is enough to get to an artificially generally intelligent system, that doesn't mean we can actually do the scaling, right? Maybe we have to build a Dyson sphere and then come back to this problem, in which case, well, maybe we can have this discussion at MetaUni Day 10 million, right? It's not a present day concern. Okay. Well, that's a valid question. I don't know the answer to that question. I'll say a bit more about it in a minute. But I think one is missing the point a little bit if you over-focus on this objection. The real thing that you need to take away from this talk is that what we have discovered in transformers is a family of highly capable learning machines obeying some universal laws. That's these scaling laws. We don't understand the laws exactly, but they're similar enough to laws that we understand mathematically that we have strong reason to think that it's not some accidental freak occurrence. It's an instance of a general phenomena which we're seeing manifested in these particular models. And some of these emergent capabilities look like reasoning. Emergent capabilities. Now, it's hard to define what is reasoning and what isn't reasoning. We'll probably never settle that question. We'll just have highly capable systems that we kind of just agree are reasoning without ever having precisely defined it. We're almost there already. But a few years ago, 5 years ago, it was possible to look at deep learning systems and argue about whether they're reasoning or not really. Nobody tends to have this argument anymore. There are enough data sets that we think require reasoning. Systems do well on those data sets, and when we examine, to the extent we can, the internal processes of those systems, it looks sort of like something we would call step-by-step processing of learned representations in a way that we can kind of agree is reasoning. We'll get better at that interpretation, we'll get better at making them work on reasoning tasks, but at this point I can have a conversation with ChatGPT about code I'm writing, and it arguably understands it better than I do sometimes, right? Or at least certainly faster. Not perfectly, but humans don't understand things perfectly either. So to say that ChatGPT is not reasoning in some fashion when you have a long conversation with it about a piece of code seems a bit perverse to me. Okay, so this is the shocking fact, this last sentence. And it's the obeying universal laws part that, to me, is the strongest argument for short AGI timelines. So let me say a little bit more about that. So I want to make an analogy to electromagnetism. So you might think that if there's a universal law around you that will make a big change to the world, surely you should notice it, and that it shouldn't just leap out of nowhere and surprise you. Electromagnetism is a clear example of why this thinking is wrong. So for centuries, millennia, we knew about lodestones, naturally occurring magnets, and we thought this was a curious phenomena, but we had no idea that the underlying cause of that magnetism, the electromagnetic force, was actually holding everything around us together, right? It's as universal as anything we experience, but we just had no idea that we saw some tiny hint of it, right? And the lesson there is that if you notice a phenomena which appears to obey universal laws, right, all magnets behave more or less the same. You can do some measurements and you can kind of see that there's patterns in the way they behave, that it's not some freak of some, like, it's not that magnets from some part of the earth behave completely differently to magnets from another part of the earth. When you see a system obeying universal laws like that, the correct inference is that maybe there's a lot more of that out there. Right? And indeed, it turns out with further study that there is a lot more of the electromagnetic force, and it explains a lot more of the world than you would suspect just looking at lodestones on your table. Similarly, when we discover scaling laws for transformer models, the way I think about it is that we have just sort of finally tapped into, with our level of technology, a very general phenomena which we were heretofore not really aware of. And that is something like advanced intelligence may be easy and universal, in the sense that sufficiently general learning machines of a wide variety of types may just manifest scaling laws and also emergent capabilities. Maybe it's just easy, and our intuitions about it being difficult are just wrong and based on the observation that evolution may have not produced highly advanced intelligence like us very often. But maybe that's just a misleading intuition. Okay, quickly on with a few other points. I want to give you a mental model for what these transformers are doing. So what if we could turn words, images, sounds, video, actuator measurements from robotic arms, etc., etc., into vectors and make a kind of linear algebra computer that could learn programs which manipulated those vectors in order to reason about the world? Well, you don't have to imagine doing that, because that's what a transformer is. It can do all of those things. Now, it isn't some super complicated mathematical object, a transformer. The roots of the idea go back to statistical mechanics, to Hopfield networks. It's quite similar to an Ising model in some ways. There were precursors, the neural Turing machine, the differentiable computer. The attention mechanism in transformers is a very simple idea to someone who studied linear algebra. So from some point of view, it's a simple system, the transformer. It's a simple algorithm which at scale produces rather interesting systems. And the point about the vectors here is the real challenge for artificial intelligence from its beginnings was intuition, right? We kind of believe that computers can do manipulations on sort of discrete entities very quickly and serially for long periods of time without error. But the thing we never knew how to do was how to get intuition into the system, right? How to learn some kind of representation, some fuzzy representation of the world, which we could then do operations over in order to reason. And the failure of traditional artificial intelligence was that it just seems very hard to represent the world in our machines in a way that's actually facilitates reasoning at a high level. If you want to put into your system that a glass is half empty, is it half full or half empty? What's the relation between those? You have to encode all sorts of things about the world that just quickly becomes completely unmanageable. So by hand, we simply failed to produce representations of the world in our machines that were useful for artificial intelligence. But deep learning has solved that problem, at least to a great extent. So whether it's intuition about go positions, or the English language, or images, deep learning produces vectors, which on top of which you can do operations. The intuition part is the part that deep learning is good at. On top of that learned representation, you can then try and do something like reasoning, and that's the part where modern systems are still not completely there. So the gap between, at least my opinion about the gap between today's systems and AGI, is the following. So I feel a bit watching GPT try and reason about things. I feel a bit like watching a calculus student who kind of gets it, right? They've watched the lectures, they've read the textbook, they kind of understand a bit how things fit together, but you can sense in their mind that it's a little bit, the resolution is a bit low. And what that means is that when they try and reason about the representation they have of the subject, they can do a few steps. But if they try and do too many steps in a row, their ideas are too fuzzy and they'll make some error, or they'll just try and put two things together that don't go together, and they'll just be lost and not know why. And that's a very common experience, and as a lecturer, what you'd learn to do is recognize that lack of resolution and the part that is low resolution, and then you bring someone's attention to it, you up the resolution until they're able to make enough serial steps without error to solve their problem. It doesn't have to be perfect, right? Physicists can use mathematics all day long and probably make very few errors, even though they don't really know the definitions. That's a fact about the universe. You don't have to know the precise definitions of things to reliably make use of them. Likewise, an AI system does not have to have completely accurate representations of the things it's working with in order to be generally intelligent. That's a fallacy. But today's systems probably don't have quite enough resolution. In the way that mathematics is perfectly clear, you can have a very good idea of what's going on and make many serial steps in order to deduce some highly non-trivial fact. Today's systems don't really have a way of getting escape velocity on that process. They'll make a certain level of deduction at a certain depth, but they're not able to sort of reach an unbounded level of deduction. In the way that Lucas was just talking about inventing writing, right? So before the invention of writing, we had a similar problem, right? We could only do deductions of a certain depth because we didn't have an external representation that was low entropy enough for us to propagate that process sort of infinitely, or at least in an unbounded fashion. It feels a bit like modern transformer models have a similar problem. They don't have some representation like that that is crisp enough to be error corrected in an unbounded fashion. So maybe that's the gap, but that doesn't seem to me like a... I think getting intuition into the systems was the hard part, and that's behind us. I think this error correction part seems like the part that machines are good at. I don't feel like this is a profound problem, and hence this observation together with the what's on the previous board here, the discovery of scaling laws, is the reason why I think we're on the home stretch, as shocking as that seems. Okay, I want to make one more point and then I'll wrap up and we can have a discussion and questions. And this is just about the economic value now tied up in the race for AGI. Not everybody with money believes in short timelines, but enough do. There's not a shortage of money anymore, which means that you might think it's crazy to scale a system until it costs $1 billion to train. But if somebody believes with some reasonable probability that they might get an AGI if they do it, it's going to be done. We're past the point where this was a question mark. The systems work well enough that enough people believe enough that we're going to run this experiment. Maybe we find out that actually we're not there yet, and maybe we need more profound ideas. But people are going to try. So this isn't the obstacle. Maybe 4 years ago it wasn't clear, but at this point I think it has become clear. So the question is, how hard are the remaining steps? Right? We're going to try. Many people are going to try very hard. Of course, we don't know the answer to that question. But to believe that there's a super hard step remaining, you have to think there's something special about the segment in between the current level of reasoning ability that transformer models have and our level of reasoning ability. And I just can't see what that is. So maybe you can suggest some ideas in the discussion. But I don't see any hard remaining steps. The only one I see is the one that I just proposed earlier. We have some issues with memory, and I mean there are things that are clearly missing from today's models, but they don't strike me as profound things. Okay, so as a result of mainly the discovery of this universal phenomena of scaling laws and its relation to things that we think are quintessential to advanced intelligence in humans, such as reasoning. So I think that within 10 years or so, we have a good chance of producing an AGI. What that means, of course, is a topic we should be discussing very intensely in the remaining 10 years. And there are seminars here at MetaUni where we do that, the disruption seminar in part, and also the singular learning theory seminar, so you're welcome to attend those. But I'll stop now and open to questions. Thanks, everyone.